Hello, this is Samurai Goblin and welcome to the third video in the ray tracing series. Last video we split up our code so that we could create a color class, and we created a screen which is just an array of colors, and we wrote values to those colors and then we saved it to a file. Today we're going to make a very simple vector class. If we're doing ray tracing, we're going to need vectors. Like vectors are at the heart of ray tracing. They're used all over the place. So let's get started. So we'll just copy this and rename it and open it up. Yeah, so we're not going to do too much code today, and we're not really going to see anything. We're not going to start ray tracing for a while, but we do need to get the code to a good point. I'm going to create a new CPP file called maths, and with header file, yep, stick it in there. Good. Tidy up. We need to call that from maths. We don't need vector there actually, because it's in there. Let's see. Too much code here. Pragma once does the same as all that stuff, and we don't need that. Let's include CMath. Okay, we're ready to go. Let's just build and run that to make sure it is still doing what we expect it to do. If I go to this folder, there we go, there's the output. It's just writing gradients to the red and green components at the moment. Right, so now we can get started on our vector. We're going to put it in here, and we'll just create a struct and call it vec. Don't know what cvec is. There we go. Now, of course, we have to be careful. If you were making a large program and then using other people's libraries and working in a team, that kind of thing, then you have to be careful with names. Something like very obvious like vec, other people may use it in their libraries. So we really should be using namespaces to keep things nice and separated. But, this is just our code. It's just a little ray tracer. We're not going to be using any libraries, so it's fine. We'll just call it vect. Vect to mean 3D vector. We're going to need 3 values. You could use double here if you're really worried about precision, but floats work perfectly fine for our purposes. That's our vec, which looks very similar to our color, except we have an alpha which we're not using actually, but maybe we will use it later on. Now we want to be able to do certain operations with vectors. So imagine we have vec1, vec2 and vec3. The 3 vectors. We would like to, for example, do this, SV2, right? How would we do that? Well, we need to overload this operator. Okay, and for this vector, we overload this operator to take in this vector and return a vector that we can put into the V3. What does that look like in terms of code? Well, there isn't an actual keyword operator which tells us we're overloading. And which operator? Well, we want the plus operator. And we need to pass in a const reference to a vector. We'll just call it V. and we're returning a vec, so we need to return, and we'll create a vec here, just like that. Okay? And what is the vector that we're creating and returning? Well, it's this vector plus the vector being passed in. So we need to do it component by component. So it just looks like our x plus v's x is the first component. And we do the same for z and y. And that's our overloaded plus operator. Okay. We also want to be able to do something like this. V1 plus 1.f. We want to be able to add a constant to a vector and return it. So let's copy this, but instead of passing in a reference to a vector, we'll just pass in a const float value. We still return a vector, but it's going to be the components plus the constant. Okay, so these two overloaded operators allow us to to write code that looks like this. We also want to be able to do something like v1 plus equals v2, and with a float as well. So we want to overload the plus equals operator. So what does that look like? Well, we're passing in here a float, and we're not returning anything, we're just modifying this vector itself. We're overloading the operator for this vector. So we're not really returning anything. We could, do that, and we'd get duplicates. If we did that, then v2 would equal v1 after it's been added or whatever. That's complicated. We don't need that. So we don't want to return anything. That's the point. So, but we want to overload the plus equal operator and pass in a float f, and we just want to add that to each component, like that. And we do the same when passing in a vector, v.x, v.y, v.z. Okay, so now we can do all these operations. Now this is just for adding a float or adding a vec, and different ways of doing it. So we need to copy this 4 times, and let's do find and replace from here. Why can't I do that? Replace plus with minus. Oh, there we go. So replace. Now replace it with multiply. Replace. And divide. Okay. There we go. So we have all the operations that we need for doing kind of arithmetic with vectors. Now there are a few other functions we're going to need. Dot product. If you don't know what dot product is, it returns a float. And we'll call it dot. Now okay, here we go. Some people like to have, let's say we have v1 and v2, I have seen this before. Some people like to make the dot a member function of the vector, so that people could do something like v3. No, sorry. Float d equals v1 dot v2. Okay, and this would be return some value, blah blah blah. Right. I don't like doing it this way because it suggests that there's some kind of order going on. It suggests that v1 is the most important, and we're just passing in v2 and doing something. So I don't like to make dot an actual member of this function, a member method of this structure. What I prefer to do is make it static, so that instead of looking like this, it would look more like this, right? Where you've just got this kind of static function which just takes two vectors and returns the dot product between them. So I prefer to do it that way. So we'll make this static. We'll pass in two references, v1 and v2. And what do we return? Well, it's just the sum of the product of each component. So we do v1.x times v2.x. And we add that to the products of the other components, z and y. There we go. And that's all it is. And I'll just go from one line. That's our dot product function. And so this is what the code will look like if we want the dot product. Okay, now there's the cross product, which is extremely useful in computer graphics for calculating things like normals. We'll get into that later on, but for now we just want to implement it. And that's only slightly more difficult than the dot product. We actually return a vector. And the vector that it returns, it has the property of being perpendicular to both input vectors. That's why it's used for calculating normals. If you give it like the two edges of a triangle, it will return the normal, or return. No, I should be more clear. It will return a vector that's pointing in the direction of the normal. The length of the resulting vector is equal to the product of the lengths of the input vectors multiplied by the cosine of the angle between them. Sorry, is that right? Cosine? No. Sine. The sine of the angle between them. Anyway, in all honesty, I have never ever needed to use the length of a vector that I've calculated with the cross product, because I always normalize my normals. I set them to have a length of 1, because that makes the mathematics quite nice. So I don't actually care about the length. But anyway, you should look it up and do a bit of research into vectors and dot products and cross products. So let's just finish off writing this function. Again, we pass in two vectors, and we return a vector that's perpendicular to both of them. How do we do that? Well, the x component of the returned vector needs to have no part of the x components of the other two vectors, of the input vectors. Okay, don't worry about that. But what it looks like is v1 y times v2.z minus v1.z times v2.y. So you can see this is the x component that we're going to return, but it doesn't have any hint of the x component of the input vectors. And we do the same for the y and the z. So the y component would be x and z, and the z component would be x and y, like in that order. And finally, just to be nice, I really cannot explain why I flip these ones. I negate this one by flipping the two parts. There is a linear algebra reason for it, but I won't go into it. There we go. Let's cram it all up into a single line and hide it away, and that will give us our cross product. Good, we're making good progress, and now all we need to do is normalize vectors. This is a very common, like I said before, we want to take a vector that's pointing in a certain direction, but it may have a length of 10 or 15.7 or something, and we want to make sure, like, constrain it to have a length of 1. It's super useful in mathematics, in particularly computer graphics. So we need to make normalize like that, and it doesn't take any parameters. So this will be just like v1 dot normalize like that, and it will go from whatever v1 is to it will constrain v1 to have a length of 1. So it's actually working upon v1. Sorry, can't spell. How do we do that? Well, really it would look like, take this vector and divide it by the length of this vector. This would be a normalized function. Okay? We're going to have to write the length, which returns a float, and by Pythagoras' theorem, we return the square root. What do we return the square root of? Can you remember Pythagoras? Well, it's the x times x plus y times y plus z, which looks uncannily like this. So all we need to do is just pass in the dot product of this with itself. Right? That's all it's doing. We dot product the vector with itself and then get the square root of that, and that is the length. Thank you, Pythagoras. So now that we have the length, we can, in the normalized function, we can divide this vector by its length, and that will normalize it. However, I don't want to keep it exactly like this, because what I prefer to do is return the length from this function, like so. So I could put like float old length before normalization, right? So after this line, v1 will be normalized. We'll have a length of 1, but we are returning the length before it was normalized, and it's just super useful to do it that way, because otherwise I'd have to do this, which would be v1.length, right? And then we're basically doing the same calculation. We're calculating the length here with a square root, which is not free, and then we're doing another, unnecessarily, we're doing another length calculation in here. There's no point in doing that, so I just prefer to return the length, because we're calculating it anyway. So this is my normalized function. Also, speaking of normalization, another thing that can be very useful is, say, like this, v1 equals, let's do v2 equals v1 dot unit. I want to have this function where I want to make v2 to be a vector that's pointing in the same direction as v1, but has a length of 1, but without destroying v1, because this can be quite useful as well. So we need to return a vec. The function is called unit, and we just return this divided by length. There you go. So we're not actually destroying anything, we're just returning, we're making a copy of this vector, but it's normalized. Okay, and finally, I think I'm going to split this function up, and I'm going to have a function to return the square of the length, which is just this, without the square root. And this is super useful. Sometimes, if you want to compare distances, like between points, then there's no point doing the square root of those distances, because the squares are going to have the same inequality as well. So if something is anyway, I won't go into it, but it's very useful just to get the square, do distance comparisons between positions based on the square of the distance between them rather than the actual square. It just saves some square root, calls to square root. Okay, so that is that's our vector class. Okay, so we can do all kinds of operations using all these overloaded operators, and we've got these mathematical operators like dot product, cross product. We can normalize and get a normalized version of it and get the length of it and that kind of stuff. So let's just see if that actually builds. Yeah, doesn't seem to be any errors so far. Let's just test it. We'll have vec v1 and v2, and let's include stream, and let's do like that. You can actually overload this operator so that you can print out a vector with this very easily, but I won't show you that. I'll just do it by hand, like this. Right, so we're printing out v1. So let's do v1 equals, let's say 1, 0, 0. So that's just x-axis, right? Let's just run that. And it just prints 1, 0, 0, which is what we expect. Now, like that. 1, 1, 1. Okay. Now, what if we do unit? What will it do to this? What's the length of this vector? It's certainly not 1, right? It's the length. It's the distance from the origin to a corner point of a cube, right? And it's not 1. It's actually the square root of 3, I guess. 1 times 1 plus 1 times 1 plus 1 times 1 is 3. So the length would be square root of 3. But we want to normalize it. We want to get a normalized version of that. So that will divide each of these components by the square root of 3. And we end up with that. So if you were to calculate the length of this multiplied by itself plus this multiplied by itself plus this multiplied by itself equals 1, because this is a normalized vector. Okay, let's do this. V1 equals 1, 2, and 3. Right, this is V2, and vec, actually let's call it 2 and 3, and vec V1 equals V2 plus V3. So what's that going to return? Well, it's going to use the plus operator, so it's going to add these two. 1 and 1 is 2, 1 and 2 is 3, 1 and 3 is 4. So we should print out 2, 3, 4, because that will be what V1 is. Okay, so basically it's all working. Let's just try let's put this back to like that. We'll just test out the plus equals operator. So we've got V1 is this, V2 is this, V1 just adds this to itself. Okay, and we should end up with the same thing. 2, 3, 4. Okay, so our operators are working. Everything seems to be working. Let's test the float operators as well. So V1, actually, V1 plus equals 1.5. Okay, and run that. There you go, 2.5, 3.5, 4.5. Okay, and multiply. There we go. It all seems to be working fine. Yep, perfect. Okay, so there we are. Our vectors seem to be working nicely. I'll actually get rid of that. That's just a test. And we haven't actually changed anything. We're not using the vectors at the moment, so we're still just outputting this picture. But we do now have a vector class that we can get started using for our ray tracer. Okay, so thank you very much for listening. This was the third in the series, and I think the next episode we may look into creating a sphere that will be ray tracing. Okay, so thank you for listening or watching, and I'll see you in the next video. Okay, bye.